All right, so welcome to the first lecture of maybe this year of yours. And today is our first lecture of the CS203 Advanced Computer Architecture, and this is 2025 winter. So I'm so glad to see you all here. So before we start, let me introduce myself. So I'm your instructor. My name is Hong Wei. I'm currently an associate professor in UCR. And you can find my website here. And if you want to send me an email, it's better to send to this address because I got tons of emails, especially those prospects these days, as you may imagine, right? So I would typically ignore most of the email unless you send to this one. So if you send me to my regular email, if I don't respond, that's normal. But if you send me to this one, there will definitely be someone responding to it. And I like to have a lot of connection with the industry. So the very first thing that I've done after I got my tenure is actually I spent my time at Google because I have done a lot of research. As you can see, I'm doing a lot of research on general purpose computing using AI ML accelerators. So the very first thing that I have done after I get my tenure is that, okay, I want to try out things at Google to see if that works. And but it also gave me a lot of insightful experience regarding what kind of people they would like to recruit at Google, and also being working at Google, I also know, okay, if I work at Google, who would I like to hire as my colleague? So I got a lot of complaint regarding this class after I came back from Google because people think this class is getting more difficult, more challenging. However, I insist to do that because I think that's the only way that I can make our students here to be really competitive candidates for companies like Google. So if you are here, I want to say you must know very beginning that this is a challenging class. You will have to do a lot of real programming, a real project. So this is not like a conventional architecture class. But through this process, I believe if you do everything by yourself and if you accomplish everything by yourself, it will be a big upgrade of your personal capabilities. And so at Google, I was working for TensorFlow Lite, right now called Lite RT. And my team, well, the team that I used to work with right now, they are actually also the one who powered the backend of Gemini. So if you happen to use like Gemini, some of the stuff are made by my colleague at Google. And before being a professor, I was a PhD student at Computer Science Department of UC San Diego. So although my home department right now is at ECE, and it seems like I'm a hardware person, however, all my degrees are all in computer science, so I'm more with you rather than those EE guys. And my research interest is general purpose computing on AI ML, and then or even ray tracing accelerators, and or anything else that make the application or our future more efficient. And fun fact about me, so like there were once I was considering a career path as a singer, but I'm here because that wasn't a very successful trial, and like a long time ago, like I haven't gone to any like cosplay event after the pandemic, but before that, that's also something that I like to do. Okay, that's about myself. Now I want to know about you. So before we know about you, I wanted to use this Poll Everywhere software, which you will be using throughout the quarter. So this is an app, and you should logging it with your UCR email with the address that shows with the QR code shows here. And if you don't have the QR code, you don't have a device that can scan the QR code, there is also an address, website address start with HTTPS on the top right of the slide. So the very first question I would like to know about you is that where did you spend your holiday season? So it seems like we got 2 of you answered. Okay, 3 of you answered. Where's that? North Pole. It doesn't look. Okay, where's that? Australia? No, that's not Australia. Okay, 13 of you. Okay. Is that Hawaii? Wait, Hawaii is gone. No one went to Hawaii? No one went to Hawaii? Seriously? Hawaii is so fun. Is that Turkey or no? Turkey is right here. Okay, it's gone. Okay, which country is that? Is that Canada? Any of you went to Canada? Okay, it's all back to the United States. Okay, West African. All right, let's wrap up. All right, so seems like we got 20 of you answered. Anyone in Japan for the summer? Who were in Japan? Anyone in Japan? You were there in summer. Okay, where did you go? I was in Tokyo, Kyoto, Osaka, Nikko. Wow, you did a pretty big round trip of Japan. That's pretty good. I was also in Japan this winter. Like I was in Kanazawa, Niigata, Tokyo. This kind of this 3 main cities. That's where I visited, and it was a lot of fun. What is that? Tell me which country is that? Which one? Who picked that one? Would you mind to share? Who would like to share about this one? You're looking around others. Is that you? Is that you? Who is this one? Okay, how about this? Anyone went there? Or is just an error? How about, okay, how about this? Toronto? Okay. Looks like we have a lot of introverts in this class. All right. Now maybe we could have another question that's easier to answer. Your most favorite computer science topic. like, okay, so it looks like most of you, okay, algorithms, learning, machine learning, right? Programming, embedded systems, LLM. Well, graphics, okay. Anything about computer architecture? I didn't see it here. Okay, awesome. All right. So then, okay, since you're not interested, why are you taking the class? Okay, core class. It showed up too fast. All right, I don't think I have to finish it for another minute. Okay, okay, I don't even have to finish. And actually, I think I know the answer in the very beginning, right? Because it's a code class. Okay, so, I want to say, I trust you guys now. Because, like in terms of integrity, I think you guys did a very excellent job in the question, in the past two questions. In fact, if you ask like generative AIs like ChatGPT or Gemini, this is also what they would tell you, right? Like what's the most topics in computer science? Like artificial intelligence, they rank as top one, cybersecurity. I'm surprised no one talking about it. Data science, big data, like data analytics, data science, and cybersecurity, right? Like how to protect your data, your privacy, like cloud computing. That's also a very big business in Amazon, right? So like, okay, all sorts of this kind of topic that people are interested about. But like, okay, where's computer architecture? Okay, then you wonder why are we here? Why this class that nobody cares is still a core class, right? So like as what I see, right? Like this is what you guys care as a computer science, right? And regarding computer architecture, your reaction is pretty much like the song we play before the lecture. Right? So that's your reaction, right? So what are the most important topics? So, but right now, if I change the question, instead of asking what's the most favorite or most popular topic, what if I say the most important topics, right? And let's see what Gemini and ChatGPT mentioned. So for ChatGPT, well, okay, Gemini give you the answer fast. First, algorithm, data structures, theory of computation. Hey, here we go, computer architecture, right? And also, okay, ChatGPT is doing a better job for us. Computer architecture and organization is actually the second, right? So what does that mean, right? Also, you might think, okay, generative AI, okay, don't trust them. They sometimes generate wrong answers, right? But how many of you know who is, well, right now, like in machine learning, we use a lot of neural networks, right? If I want to say, I want to make a word or say who is the father, who are the fathers of neural networks, what are the names pop up in your mind? What? Jeffrey Hinton. What else? Yann LeCun. What else? Okay, I don't recall his name either, right? But this is Jeffrey Hinton. That's here from what he said. So Jeffrey Hinton actually won the Turing Award in 2017. No, 2018. And this is what he mentioned in his Turing Award talk.
I think a lot of the credit for deep learning really goes to the people who collected the big databases like Fei Li and the people who made the computers go fast, like David Patterson and others.
Okay, so he mentioned two names specific, right? One is Fei Li. She made a lot of breakthrough in data storage and efficient data supply. And the other one, Jeffrey Hinton mentioned, is actually David Patterson. Who is David Patterson? Did you see his name somewhere? How many of you check our website? The course website before you came to the class? You? Did you find the name of David Patterson? Who is David Patterson? So if you check the textbook we are using, Computer Architecture, a Quantitative Approach, is written by John Hennessy and David Patterson. So what does that mean? Actually, Jeffrey Hinton gave a lot of credits to us because without computer architects make computation fast enough, there's no reason why neural networks can success. And in fact, when I was really, really young, 25 years ago, that was a time, there are lots of neural networks paper. And then a decade, there's nothing. And the reason is because 25 years ago, people have the consensus. Neural networks is not something possible. However, what really made it possible is computer architecture. So that's why computer architecture is so important, because without computer architects, there's no way deep neural networks, as long as the large language models that we are using every day, you are using to write your assignments every day, right? They are not going to be there without this class. So I want to say, computer architects, we are the so-called hidden figures. So it's not something that people would pop up immediately in your mind as your favorite, as something popular. However, without computer architects, none of this, like big data analytics, or like neural networks is going to success. So that's why we want to learn. As a computer scientist, we want to learn computer architecture. And that's why this is still a core class. So I mentioned computer architecture is so important, but what exactly is computer architecture? So it's very important. You know how to use this generative AI, and I like to use it, and I love to use them, right? So let's ask them first. So ChatGPT, computer architecture. Okay, let's wait for a little bit. Gemini is faster. Computer architecture is all about how computers, right? So like instruction set architecture, blah, 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 right? So, like that explains computer architecture a lot, and ChatGPT, okay, is so slow in generating the answer. Never mind. But let's look at the easy definition from the dictionary. So computer architecture is so important in a way that if you go to the Webster dictionary, it also lists computer architecture as one of the items here, saying that the manner in which components of a computer or computer system are organized and integrated. So a lot of people might thinking about, okay, like how ALU works, like how binary system works is part of the computer architecture. I want to say no. As an architect, or say as a system architect, we are actually the ones who guide how to build a computer, what kind of components we want in a computer. However, we are not actually the ones who build this components. So computer architecture is actually more abstracted or higher level than you can imagine. So, and a lot of us have the misunderstanding about like, okay, computer architecture is all about hardware. However, that's not the truth. And in fact, in this class, I'm going to teach you how can you use the knowledge of computer architecture to make your program fast. But before we start the journey for this quarter, I want to let you know, maybe you really need to learn more about computer architecture. So we want to have a small activities, some small activities right now is that I would like to invite everyone to stand, if you could. And then I would have the questions like this. If you think the answer is correct, go to the left-hand side of the slide. If you think the answer is wrong, go to the right-hand side of the slide. And I have maybe like 10 or 11 questions. If someone can survive at the end, I will give you a gift card. Okay, so processor and memories are essential for most general purpose computers. 5, 4, 3, 2, 1. Okay, so you got it. Okay, that's a very good thing. Second question, Moore's law is still alive. Okay, 5, 4, 3, 2, 1. All right. For people on that side, please go back and have a sit. Okay, we have 5 remains. Okay, gift card, gift card, gift card. Okay. On the same machine, programs with fewer lines of code will have shorter execution time. Okay. Are you sure? Are you guys sure? Okay. Now, on the same machine, an algorithm with lower computational complexity will have shorter execution time when solving the same problem with the same input. The same machine, algorithm with lower computational complexities. Wow, we're learning complexity, right? Like in algorithm class, how many of you are struggling with getting the right complexity to prove the complexity, right? Why are we spending so much time to learn it? It should be right, right? But unfortunately, the answer is no. Okay, 3 of you. Now, on the same machine, algorithm implementation with the same computational complexity will have similar execution time when solving the same problem with the same input. Now we are talking about complexity with similar complexity. See, each question is even better and better defined. Okay, are you sure? Okay. Okay, not yet. You have to pass all of them. Okay, next question. Bitwise operators in C, right? A lot of people say, well, let's try and or, right? How many of you have experience of testing and or? Like, yeah, right? Make sense? Would that faster? Would that be faster? Okay, you still say no? Okay, good choice. Now, algorithm complexity is less important if we have reached parallel processing capability. Still no? Like complexity still matters? Okay, you think the answer is wrong? This is right. Thank you. You're done. Yes. You know, every time I can save 20 bucks. And this, I do have other question. The smaller size of a transistor, the small power consumption of it, like it means that if we have better processing knowledge, the power consumption is going to reduce. The answer is no. And GPUs are not limited by Moore's law. The answer is also wrong. and the performance growth of the recent GPU architecture does not match. And okay, so you might think about, no, this is completely challenged my understanding about the world of computing, right? Isn't that right? Especially like people who believe like algorithm or complexity is their Bible. But the answer is those are wrong. And well, I won't say those are wrong. Those are not realistic. That's probably the better word to describe it. But let me show you the evidence. First is algorithm and computational complexity good enough? So I want to show you a demo. I like to have demo in the class. And in the rest of the lectures, you will see, in the rest of the lectures throughout this quarter, you will see a lot of code demos. And that's how I connect your knowledge with hardware together with your coding. Okay, so tell me about this code. So this code, I can consider it for two segments, right? The first code section is about if, the if start by the if statement, right? And the if statement also contain a code block saying, well, if the option is true, then I will do sorting, right? And the second code block is a for loop, and the C is a constant. And inside that, there is a statement that, I think I missed an if there. So if data is greater than t, right? Then I do some plus plus, right? So tell me about this code. What's the computational complexity if the option is false? What's the computational complexity if the option is false?
Should be just linear, and you're doing a pointer chasing, right? C moderate size.
That's not pointer tracing, right? That's not pointer tracing, right? Yeah.
It's cool.
Yeah, so it's order n. Okay. Do you guys all agree? What if I have the option as 1 or true? N log n, right? So this part is n log n, this one is order n, right? So if option is set to 1, the computational complexity is higher. Do you guys all agree with that? And we are doing more work. Do you guys all agree with that? So if you show this code to the algorithm professor, they will tell you having the first part is a bad idea because you are doing redundant work in the algorithm's perspective. Do you guys all agree with that? Yes? Okay. So let me show you the demo. Hello? Oh, shoot. I just changed the address. Okay, let me show you the demo. Here we go. So in this class, we will intensively use Jupyter Notebook. So including your homework, all the assignments. So if you are not familiar with Jupyter Notebook, this is also a very good chance for you to get familiar with it. So this is exactly the program that we have seen, right? So this is the calculate sum, which is the for loop part. And the driver of the code, it actually contains two parts, right? First, I initialize the data, right? And then there is an option here, and there is also calling the for loop for the calculate sum, right? So that's exactly equivalent to the code that we have, right? And right now, okay, let me rerun the whole program, and then let's try. If I rerun the whole program with sorting, and when I say, if I sort the data first, and I would need 0.1 seconds to finish. However, if I decided to not sorting the data, it would take 0.5 seconds to finish it. So it's actually about 4 times more if you don't sort the data, right? So sorting, although its computational complexity seems to be higher, but it's actually a better idea. Okay. So are you convinced that there are cases where the computational complexity doesn't really represent your execution time, even though it's exactly the same problem we are solving? Do you agree with that? Right. So for this case, on the same machine, programs with fewer lines of code will have shorter execution time. First of all, fewer lines of code. For example, if I disable the option, right, that's the case where we have fewer lines of code, right? It actually has longer execution time. And also, computational complexity doesn't really 100% related to your execution time at the end. Okay, so now, the second thing we want to show. So for the left-hand side and the right-hand side, what about their complexity?
They're the same, but the left side should be faster because it's coalesced.
Is what?
Coalesced reads.
Okay. So both of them have the same complexity, right? However, if we run them, right, this is what we will see in terms of performance. So again, I'm going to run this code. So here, right, this is exactly the program. The left-hand side and the right-hand side, as the slide shows. Right, the only difference is the left-hand side, we start with 4i, and the other one start with 4j, right? And let's see what's the difference in their computational, the time that needs to compute. So for the first case, I start with I, right? That would take 5 seconds. And let's see, if I start with j, how long is it going to take? So it would take almost like twice the amount of the time, right? Again, the same input, the same problem, even the same complexity. If your implementation does not consider the underlying architecture and the underlying architectural optimization, you are going to lead to very bad performance. So for this one, on the same machine, algorithm implementations with the same computational complexity will not necessarily have similar execution time. Okay, so bitwise operators, right? So this is actually, I would think, this is something a lot of grandfather old programmers would like to check how your capability of if you can ace the C programming language, right? So a lot of people get that implication that, okay, if this is what I get when I was tested to enter the company, should I code in this way, right? So the left-hand side and the right-hand side, they are both equivalent, right? And in some companies, right, when they test you, you write the left-hand side code, they will think, okay, this is so naive. You must not be an expert in the C programming language. However, is that true? Is that true? So I want to show you another demo. So another demo is about this, right? We have 2 different versions of the swap. The left-hand side, I would say the naive swap, or say the register-based swap. And the right-hand side is the exclusive OR-based swap. And here, I'm going to show the difference. So I have a program. I'm pretty much like swapping array content using this swap function. And as you can see, if you use the naive swap, it's actually slightly faster than the exclusive OR swap. And if you don't trust me, you think, okay, this is just a coincidence, right? We can run it one more time, right? If you run it one more time, right, the exclusive OR is still slower. And I will tell you, no matter how many times that you run, the exclusive OR is always going to be slower. So what does that mean is that bitwise operators does not necessarily make your performance better. And in fact, in most cases, they are harmful. In many cases, they are harmful. So the next time, if some of the engineers saying that, why don't you use bitwise operator, you can say, your code might be slower, right? So I'm writing performing code. Now, the fourth demo I'm going to tell you is about this. So sorting, right? We have been talking about sorting a lot, like quick sort, unlock n, right? Now I'm going to tell you another algorithm that does sort. It's called Bitonic sort. So Bitonic sort does sort using this loop. And if you check the structure of this loop, the first one is basically an order n loop. And this this one is basically an order n loop. And for the outermost two, if you check how they manipulate their index, this one multiply the index by 2 every iteration. And this time divided the index by 2 every iteration. So you can imagine this 2 is actually log n, right? So this is log n, this is log n, and this is n. So the computational complexity of this algorithm is actually n log square n. So which side has higher computational complexity? The right-hand side, right? The right-hand side. So now let's continue our demo on this. So if I run this on a GPU, what would happen? So here's a quick sort for the GPU. As you can see, there are some GPU functions. And here is the Bitonic sort for the GPU, which implements the same algorithm that I mentioned here. And right now, I'm going to show you the runtime of it. And all right, so as you can see, if I use Bitonic sort to sort this amount of numbers, it takes 0.1 seconds. This is like light speed. However, for quick sort, okay, this is definitely more than 0.1 seconds. You guys all agree? And you might think, okay, is this a bad GPU? It's actually an RTX 4090, right? Before the end of the month, this is still the best consumer card you can get from the world, right? So what does that mean is that, okay, even though Bitonic sort has higher computational complexity, but it actually works pretty well for the GPU architecture. However, for the quick sort, even though I'm trying to come up with a lot of words, right, it still takes this amount of time, a lot longer than Bitonic sort to finish the same sorting. So what does that mean? Is algorithm complexity is actually less important if we have rich parallel processing capabilities like GPU. So for all of this question, right, this algorithm questions, a lot of you consider yourself as a very good programmer. You're so familiar with the algorithm. However, sometimes you will feel that you get a lot of challenges when you enter a commercial, or when you are doing commercial products. Because in fact, those algorithm complexity, they just give you a reference regarding the growth of my time. However, it doesn't give you the right reference of the absolute execution time. So if you consider algorithm complexity is everything about the performance, it's actually wrong, and run in a way that is very far from the real. So the reason why I want to talk about computer architecture, and I think computer architecture is important, is because most of the time, when we don't understand our computer, we consider it as some kind of beast that we thought it was and use it in a wrong way, right? So for example, if you see this tail, and if you ever play Pokemon, right, you might think this is a Pikachu, right? However, Pikachu is not the only one who has that tail. What if you got a mimic, right? Then you should totally use a different ways of attack, right? Like for Pikachu is an electro type. However, for Mimic, it's actually is a cycle type attack, right? So if you don't use the right one, you are going to get the wrong effect. Another example I can give you is like, okay, washlet, right? How many of you ever use this one? Okay, right? However, if you never use washlet functions, the washlet is just a waste of money. And it wastes more power, wastes more energy, wastes more money, right? Or are you going to buy your grandfather a Tesla? Are you going to buy your grandfather a Tesla? Why not? Tell me why. They might break down the car? Well, why do you think they might break down the car? See, right? So here's the thing. If you don't understand your computer architecture, if you don't understand your underlying computer architecture, you will be like your grandfather who crashes the Tesla, right? So the first takeaway, why do we want to take CS203? Because algorithm complexity does not work well on real computers. So let's start talking about computer architecture. So the big picture of computer architecture is actually the von Neumann architecture. So what is von Neumann architecture? Can some of you answer that? What's your understanding about von Neumann architecture?
You have an ALU.
You have an ALU,
Memory.
memory.
You have peripherals.
You have peripherals.
Memory.
Is ALU the right term?
CPU, control processing unit, CPU.
Okay, you have a processing unit, and you have memory, right? Agree with that? How are we going to use that?
Data path.
Higher level. Higher level perspective.
How are we going to use the processor memory?
Yeah, processor and memory. What are their functions?
So you store all the data on the memory.
All the data in the memory, just data? Instructions and data, everything, right? Everything that must be represented in binary, they must have a place to hold in the memory. And then
you take whatever is necessary to transfer it to the CPU.
Okay, whatever is necessary is transferred to CPU, and what does CPU do?
Do the computation.
Computation.
Yeah, and the result is then again stored back to the.
Okay, if there is additional memory access, we store it back. What else? Storage. Okay, but is that everything that the CPU needs to do?
It should also have an I/O.
You should always have an I/O. What else? You missed one big point.
Instruction fetch.
Instruction fetch. Okay, that's close.
Pipeline.
No. So after you fetch the instruction, after you are done with the instruction, what else you do?
Decode the next.
No, you need to move the instruction pointer, right? Otherwise, your program won't move, right? Your program won't move on, right? Okay, but sounds like you guys kind of like get to the point what a von Neumann architecture, right? So in fact, one of the questions we ask is processor memory, they are everywhere, right? So if you take a look of the desktop computer like this one, right? It actually has a motherboard and also a socket for a processor. So how many of you have the chance of seeing inside a desktop computer? Okay. If you haven't, I actually brought some components here for you today. So this is a motherboard that, oh, by the way, be careful. This one is still functioning. This is a motherboard from a real computer. And in your computer, it's pretty much like this. And there is a heatsink. So under the heatsink is a processor. So this is an Intel processor, like this one. And like on the back end, there are a lot of like soldering pins where you can attach to the socket here, so then they can communicate with the motherboard. And also, here you will see the memory sockets, right, where you can have the memory, right? So okay, I will pass along. Okay, so this is the processor, and this is the memory. And on the other side, like for this one, this is a relatively new one, so we don't have any hard disk drive. Instead, we use solid state drive to store our persistent data. And okay, also heat sink. You can pass it along. And some of you might be thinking, okay, most of the time I don't do computing using computer. I'm using a GPU, right? Where's the GPU? So GPU is actually connect to your processor with some of the expansion slots, right? And this is an NVIDIA Tesla GPU for a few generations ago, but still a pretty powerful one. So you can feel how heavy is it. And I also have a less powerful GPU from AMD. So for this one, because it's less powerful, because it's cheaper, it's actually not something I'm in use. So I actually tear it down. So you can see under the heatsink, there's also a GPU die. Right, pass it along. And yeah, you can pass this motherboard. Okay, I would give you one job. Can you put everything in a box? Right, so this is a desktop computer, right? And you can see all the components, right? And typically there is a processor socket, there are memory slots, and there are places for peripherals like GPUs. And some people think about, okay, data centers, computers, are they different? The answer is that yes, they are slightly different in a way that each of the motherboard can now host multiple processors, has way more DRAM slots, and also peripheral space. And you might think about, okay, laptop computer, they are spatial. However, if you tear a MacBook Pro like mine, you will tear it down, you will find out, well, it still have the same components, but package them together. So with the same chip, you will see like a multi-chip package, which consists of a processor plus GPU plus DRAM. And also have soldered Wi-Fi modules, peripherals like solid state drive and I/O connectors. Like the iPhone 15 Pro that I have, it also have a assembly of the processor plus GPU plus DRAM, as well as some of the solder chip for NAND flash and network modules or some of the sensors. PlayStation 5, okay, it's still a computer, even though it's a game console. It still have a processor plus GPU. And this ring looks pretty fancy, but it's actually DRAM. And also peripherals like SSD. And some of you might be thinking about, how about Switch? It's still the same thing. For Switch, it also have a processor plus GPU and some of the DRAM chips and some of the peripheral, like for example, like NAND flash for storage and networking. All right, Tesla, even a Tesla, right? This is the main assembly for the Tesla. The Tesla has two processors because for cars, we actually want redundancy for safety. So they actually have two processors. If one is not functioning, the other one can take over. And surrounded by the processor, there are also DRAM chips and also storage as well as power management IC. So even a Tesla is still a von Neumann computer, right? So everything is a von Neumann computer. And in von Neumann computer, you will see processors and memories are everywhere. And why processor and memories are everywhere in a von Neumann architecture is because this is how von Neumann architecture works. So first of all, what John von Neumann said about is, if we want to have a reprogrammable computer, this is how it would work. So first of all, your code, or say your program, consists of instructions and data. So the instruction would describe what kind of control what kind of flow control or what kind of computation you want to do. And the data here means the initialization data. And so when you compile your program, when you generate your program, these are the two essential components in the very beginning. Of course, you might know that the data could evolve and you can allocate more and more data. But in the very beginning, even a compiled program, a program already have an instruction section and code section. And if I want to execute a program, the very first thing that I will have to do is to load the compiled program and data from the persistent storage to the main memory. So in the very beginning, when John von Neumann talked about von Neumann architecture, there's nothing really about the storage, because at that time, people were not thinking about storage as so important. But right now, as you can imagine, right, we use storage every day. So there's no reason why we should not include storage in the picture. So whenever you want to load the program, execute a program, you load it to the main memory. And what happened is that in your processor, the logic in your processor will specify which location in the memory should I fetch the next instruction. So that's called program counter. So for example, if I have a program counter like this 104064, and then it will go to the corresponding address to fetch that instruction, and then decode that instruction. Like for example, this one we know it's a subtraction, and then prepare the register values with the corresponding values as the inputs for the target functional unit, and then finally generate the result, store it temporarily in a register. And in the future, if you want to store the data back to the memory, you can also transfer the register value to the memory. However, don't forget, after you are done with an instruction, it's most of the time your program has to move to the next instruction. So when you move to the next instruction, you will fetch a new instruction. So the first question, everyone gets it right. Processor and memory, they are essential. However, the reason behind that is because modern computers, no matter it's as small as a switch, no matter it's as small as an Apple Watch, or as big as a Tesla, or some data center computers, they are all von Neumann architecture. Okay, so in von Neumann architecture, the microprocessor is just a collection of functional units. And so this is the concept of processor. And the instruction set architecture defines what the processor should support. So it actually the instruction set architecture, for example, like x86 or ARM, this kind of instruction set architecture, that actually define the spec, the features that each processor should support. So this is the basic concept of processor. So you can also imagine the instruction set architecture is pretty much like when you play the game, right? Like most of the time, you don't really care the exact, like, okay, most of the time, if you know how to use this like ABXY, you are able to play most of the game, right? The reason is because they abstract all the features of the game or each Pokemon with these 4 keys. So the same thing happened to the processor, is that the instruction set architecture, they basically defines each processor should support this set of instructions, regardless how they internally implement the hardware to support it. So that's the concept of instruction set architecture. So that's where we are. However, there are challenges in the von Neumann architecture nowadays. That's actually Moore's law. But let's talk a little bit about Moore's law first. So before we talk about that, what's your understanding about Moore's law? Okay, the number of transistors within the same area will double every 2 years. Okay, so that's actually the implication of Moore's law. So, but in Golden Moore's original paper, he didn't mention that at all. There's people just use the figure he drew. So, you know, like as a computer scientist, as a computer architect, that spent 20 seconds to go through that paper. So first of all, in that paper, they are talking about ICs, integrated circuits. They are increasingly popular, and they are well established. They are more reliable. They could be made even smaller. And that figure here that you show is actually where the Moore's law comes from, right? It's horizontal axis is the year. The vertical axis is the log2 of the density of the chip, right? So based on that, people extrapolate the line and saying that, okay, based on that, right, every 2 years we are going to see the double of the area, right? So, like some of the people, they don't think Moore's law is alive, right? Some of the people saying that Moore's law is alive and well. Who is more honest? Who is more honest? This guy who just retired or this guy who just announced a new product? Okay, so, we are scientists. We should conclude based on the facts. Remember, Moore's law is talking about the density of the chip can increase every 2 years, right? So following the path of Gordon Moore, I also draw this one. Horizontal axis is the year, and the rightmost is 2025. And vertical axis is the density of the transistor. Similar to Gordon Moore, I also use log scale. So if the line is straight, it means that we are still following the Moore's law's path. So each of the dots here is the density of the chip that has been produced of every year. So these are the data that I collected from the public open source. If I draw the line, it's still straight. What does that mean? Moore's law is still alive. It's still alive. So if someone saying Moore's law is dead, he is actually a liar. He is actually a liar. However, he is not too far away from being true. It's alive, but we all assume it's going to die at some point. And in fact, even though it's more alive, it doesn't make any difference anymore. So Moore's law is still alive. However, if you look at the chip performance, like the CPU performance, in the past 10 years, it only goes up by 4.15 times. And this is the growth rate supposed to be if the CPU performance can scale with Moore's law. So the problem here is not about Moore's law is dying. The problem is about, even though Moore's law is alive, the processor speed cannot improve anymore. So what happened? So these two guys, the left-hand side is John Hennessy, and the right-hand side is David Peterson. They actually won the Turing Award in 2018. Let's hear from what they said.
So the first thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
Okay, so what they want to tell you is, okay, in the past, right, in the past 30 years, in the good old days where Moore's law can consistently support the growth of processor, you guys, right, you never care about what the computer really does. You just think, okay, I write my program based on the algorithm complexity I learned. And even though it actually makes very bad use of computers, because of us, computer architects, we made the processor faster and faster. So even though your program were initially so slow, at some point, at some generation of the processor, it will become fast. So that's why a lot of the software programmers, they don't think we need to care about computer architecture, because we just make those guys so comfortable in their life. However, as what they said, it's over. However, why? Even Moore's law is still alive. The good old days is over. And the reason is because the power consumption per transistor is actually killing us. So The left-hand side is the power consumption of the latest generation of NVIDIA GPU, which is supposed to use a better process technology by TSMC. And the right-hand side is actually Intel's power consumption per transistor using an older generation of the process technology. As you can see, the newer generation of process technology, each transistor would actually take more power than the earlier transistor, earlier process technology. So what does that mean? Right now, even though I can put more transistors within the same area, each transistor is not even making lower uses of your power. In fact, it's going to be hotter. It's going to be more power consuming. As you can imagine, that makes your chip really hard to dissipate their heat and make it really hard to fit in your computer. And that's why, even though newer process technology seems to increase the density, however, we don't actually want that kind of density because it just makes the problem even worse, right? In fact, this was originally already a problem in early 21st century. So at that time, people discovered it's already hot enough for us to heat up a good amount of things. For example, the most one that you can find on the YouTube is how to cook an egg using your processor, right? And if you don't do anything, people would imagine if you keep increasing it, it will become as hot as your sun. So what really happened is that we control the power density. But as you can imagine, if each transistor is going to be more power consuming, how many transistors can you put in a chip? It's not going to be a lot. So that's why we are not seeing the performance improving, even though Moore's law is alive, because each transistor is more power consuming. So now, people try to find other options to use available transistors. For example, you can exploit thread-level parallelism of data-level parallelism. So that's why we are seeing multi-core architectures. We are seeing GPU architectures or Google's TPU architectures. So right now, you can imagine in your computer, it's not only the conventional processor, but you are also having a lot of new accelerators. For example, GPUs that are originally for graphics and TPUs that are for tensor algebra, and FPGA, which is a programmable accelerator. However, does that solve the problem? The answer is no. It actually makes the problem even worse. If you look at this, right, everyone is connected to the memory. So the new bottleneck will become the memory, right? So we are still facing challenge, even though we have GPUs or TPUs. And in fact, putting all together of this would actually make the performance problem even more serious, right? And the other thing, like NVIDIA, I don't like Jensen Huang, to be honest, because I feel, as a scientist, I feel he is keep fooling people. So he is giving you the impression that, okay, NVIDIA can surpass the limitation of Moore's law. But in fact, I'm telling you, no, they do not. For example, if you check the power consumption, right? So in H100, each chip is 700 watt. In A100, the Ampere architecture is only 400 watt. So what, and if you check the transistor, per transistor power consumption is going up, right? So they are not. So the only way and the only reason they seem to be available to surpass the performance or improve the performance is just because they use better heating technology, like heat dissipation technology, or larger heat sink, right? Like this is the heat sink for H100. However, for A100, it's just like this, right? It's a lot larger, a lot space consuming. So it used to be the case that I can just use a 2U server to fit 8 GPUs. However, right now, people have to go to like 4U or even large data center servers to fit the same number of GPUs. Question?
When you mentioned the previous slide, like multiple components makes it worse, then why are they still making those multiple components if it makes it worse?
So it make it worse, right? But it make it worse in a case where your computation is memory bounded after you have accelerators. So, however, if your computation, if you have a workload that is compute intensive, then it's still helpful. So, for example, if you don't have a lot of data sharing among different units, that's still helpful.
So it's basically kind of like moving the problem to something else.
It's actually shifting the problem to something else. Okay. So GPUs are not limited by Moore's law. No, they are. Right? That's the biggest lie that I ever hear from Jason Huang. Okay, so where are we now?
The future is parallel. Single cores are not getting any faster.
Okay, so sadly, single core is not getting any faster. In fact, even GPUs are not enough, right? So this graph, horizontal axis, is the performance of best CPU and best GPU at each year. And they are represented by flops. And the red line is the computation power represented by floating point operations per second that we need to finish training a machine learning model within a week. A week, that's not too long, right? That's actually pretty long, right? So if I give you guys a week to train a model, here, the red line represents the computation power we need. And it's actually a huge gap between the performance of the best GPU and the demand of the model. So because of that, right now, we are having a lot of hardware accelerators to power the growth of AI ML. So, but what does that mean is that, okay, processor memories are essential for modern computers. However, their performance are improving slowly. So we are now falling behind the demand of applications. And even though Moore's law is alive, but if we cannot control the power consumption per transistor, Moore's law doesn't make any sense anymore. And also the problem is because we have a huge performance gap between memory and the processing speed. So right now, even though you have a lot of hardware accelerators make your computation a lot faster, the bottleneck may already be on the memory side. So even though you add more accelerator, add more GPU, your applications are not going any faster. So we have to rethink about programming as computers become more parallel, heterogeneous, and application specific. So in this class, I have a vision and I have some missions. First of all, as the vision part, we want to be programmers who can write efficient programs that save time, power, energy, and carbon footprint. And your mission is to understand or using the knowledge of computer architecture and the general guidelines to identify performance problems and design solutions to tackle the challenges of real-world applications. So this is what I envision you guys will be able to do after taking this course. So we are right now in a heterogeneous computer architecture, and in this class, we are going to cover materials regarding performance, memory, processor design, as well as parallel. So this is a tentative schedule, and we were going to cover the performance, memory, processor, and parallelism. And you can find the exact schedule on the course website. And let me talk a little bit about the learning experience, which you might care the most about. So as you already feel, this class has a lot of activities. And in fact, this is not only for the first lecture, it will be continued throughout the quarter. So most of the lecture today, my feeling is like, it's pretty much like watching a pretty good show, right? But you know, sometimes when I watch a show, I feel sleepy, or I just don't feel like I am thinking. So I expect the lecture to be some kind of game show. Like I'm the anchor, I'm the host, and you are the player. And you may be really happy, right? So this teaching method is called peer instruction. So the peer instruction is a method that I would have some of the activities pretty much pop-up questions like I give you today. And each question we will go through 2 different phases. The first phase is an individual thinking phase that everyone should be silent and think about the question and vote. And then after the initial vote, based on the result, we would decide if we want to go to the second phase, which you guys are going to talk in small groups and then reach a consensus before your second vote. And if we still see the answer is not converging, then we will go to the whole classroom discussion. So this is a process of read, think, and discussion, because before each of the pop-up quiz, we want you to read so that you would have some basic knowledge before. So to force you to read, unfortunately, I know this is the only way that I can force you to read is to have reading quizzes. So before half of the lectures, and actually there is a reading quiz due before the next lecture on Thursday, you would have to read the assigned material. And this would account for 15% of your grades. And it will be done. You can find it on the grade scope already. And at the time of the lecture, set up the poll everywhere, which you already do today, and to answer those questions. And so for the peer instruction question, it's pretty much let you engage. And as long as you can answer 50% of the question, which means that I really allow you to be absent for 50% of the time if you want, right? You can still get a full credits for an assignment, right? And this class, we do not have any remote options. And we also have assignments based on using Jupyter Notebooks. So if you're not familiar with that, try to use it. And we actually have prepared a cluster for you guys to use. And you should watch this YouTube video before you start the assignment and regarding how to use the environment that we provide you. And so I envision this is probably the amount of time that you should spend, like 3 hours of 3 hours of the lecture, 4 hours of the reading and papers, and 5 hours of the assignments each week. So logistic, change it a little bit from the last time. So let me think why this is, oh, okay. So this is actually the old version. Oh no, this is the right one. Okay, awesome. Okay, so we have 50% of reading quiz, and we will drop your lowest too. And assignments and midterm, we are actually combining together as a single item. So we will have a total of, we will have a total of 8 assignments plus your participant, that's actually 9. And also plus the midterm, that will be 10, right? So you will have 10 assignments including a midterm. And we will drop your lowest one within this all items. So for example, if I bomb the midterm, okay, it will be dropped, right? However, if I ace the midterm and I feel like at the end of the quarter, I have a lot of other things to do, you can actually choose to skip an assignment, right? So this gives you a lot more flexibility in optimizing your grades. And for the final exam, we still have to have something that fairly evaluate everyone. So it still accounts for 35%. So that's pretty much the grading policy, right? 15% of reading quiz, which we don't have any time limitation on it, as long as you can finish it before the deadline. And you can open the book, find the answer while you are answering it, right? Because the only reason why we want you to have reading quiz is because we want you to read. And for the assignment and the midterm, right, they are mixed together. So even though you bomb one of them, that's not going to kill you, right? And then the final. All right. So here's my information, and we also have a Google Calendar that tell you when is the lecture. So be sure to subscribe it. And here's the website. So everything, don't ask me for where to find what. Everything is on the website except for one thing. So that one thing is actually the Discord, our discussion group. So you can find the course agreement inside our Grayscope, and it's actually due this weekend. So some of you might think, okay, why am I wanting you guys to sign the course agreement? Because in the past, I do find cheating cases in the class. And surprisingly, the school give me an answer like, have you ever told a student that referencing online solution is cheating? Do you have evidence of that? So that starts my reason why I want to have a course agreement with all of you, making sure that something that I think every of you should know, should understand, is indeed agreed by you. Okay, it's not because I don't trust you, just because in the past there are so many cases like that, making me feel we should protect each other. Right. So you can find the link of the Discord in the course agreement once you have signed that. And without signing a course agreement, I'm not going to give you any credits for the class. So this is a must. Okay. So I do have office hours. It's Wednesday afternoon in my office. All right. So other than that, I think that's pretty much about it. So I like teaching, so that's why I'm here, right? This is a low-paid job. Like I get only 33% of the salary I got from Google when I get back from Google, right? But the only reason is because I really like to teach students. I want to see you grow. So I hope at the end of the quarter we can all take a photo like I did with all my prioritized students. All right, so before you leave the classroom, make sure that you check our website and log into Data Hub, Grayscope, Discord, start your first assignment, and the first reading quiz is actually due this Thursday before the lecture, and unlimited time before this Thursday's lecture. And programming assignment 1 is released, assignment 1 is not yet released, and they are all on the Data Hub service that we have. And if you want to find a link, how to start this assignment, it's all on the website. All right, other than that, I will see you. Question?
So we're going to use the Canvas anymore?
We don't use Canvas at all. Don't you feel like it's a terrible tool? Yeah. Okay. It's so once you sign a course agreement, you will see that. Okay? All right. Other than that, I will see you on Thursday. You can take me anywhere. You make me feel like I'm loved by somebody.